record. I realize probably don't need to necessarily go back and watch it again, but I do like to have it if people are ever out. So the parent function for this, Grace, is it Grace or Gracie? Either one. Which one do you prefer? Okay, Gracie. What is our parent graph for this one? Perfect. Good. So our quadratic, y equals x squared, is our parent graph here. We have several transformations. Chase, give me one of the transformations. Down 6. Evie, give me another one. Right 2. Okay, and there's one more. Michelle, what's the last thing that happens? Good. Reflected. Gosh. Over the x-axis. This is driving me crazy. The smart notebook program doesn't like working with this thing very well. Okay, so we have all of these things. So y equals x squared, that's our parent graph. That's what we're starting from. Now, what we need to know is we need to have the y equals x squared graph stored in our brain so we automatically know the point. I have done this for like 10 years in a row. I can just picture it in my sleep. You guys have probably done at least x squared enough that some of you might know how, but so let's think of just y equals x squared. Technically, we could just make us a chart and plug in a bunch of numbers to this equation and it would eventually graph it. But a lot of times you get numbers that are way off the graph and it takes you a while to figure that out and it takes a lot longer. But y equals x squared. If I just plug numbers into y equals x squared, for example, I'm going to start with negative 3. What is negative 3 squared? It's 9, right? Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. Okay? These are the points of the parent graph for y equals x squared. If you're ever unsure about what it is, you can go back and make yourself a table. But hopefully as we do more and more of these, you just kind of have it stored in your mind where you don't have to actually write that down. So you just know negative 3, 9, negative 2, 4, negative 1, 1, 0, 1, 1, 2, 4, 3, 9. So I'm going to put little dots at all of these points. This is not my answer, but this is where I'm starting from. Now, whenever you are doing transformations for this, you might want to make yourself a little note here. You must do reflections and expansions or compressions. First. Okay, so you have to do reflections and expansions or compressions first if you have them. So we do not want to move this down 6 and then reflect it because it would look a lot different than what it's supposed to be. It's kind of like order of operations. Reflections and expansions and compressions are always multiplied. And you do order of operations, you have to multiply before you add or subtract. So the first thing we're going to do here is we have to reflect this over the x-axis. So I'm going to take all of these points right here, and I'm going to flip them over the x-axis. So that would look like this. I'm going to use some red points here. And so now my red points are the points that I'm using. So I have taken my x squared and I have flipped it upside down. Okay. Then, and it really doesn't matter. I know this one only had a reflection. It really doesn't matter whether you do reflections or expansions or compressions first. You can do either one of those in either order. But they must be done before you shift anything up, down, left, or right. And now I can move these points down 6 and to the right 2. Typically I do those at the same time because that's just a slide, so it's easy to do. So all of these red points, they've got to go down 6 and to the right 2. So like that vertex point there goes down 6, right 2. This point's going to go down 6, right 2. This point goes down 6, right 2. And you'll notice some of your points are going to go off the graph. That's okay. Just put whatever will still fit. And I'm going to draw a line through that one because that is my final answer. Now, the more we do this, the better you may get at it. I can do this without having to do any of the intermediate dots that I drew there for this one. Anyway, I know it's upside down. I know it's down 6, right 2. I can do that without drawing all the dots. But now some of the more complicated ones I still draw all the dots for. So as you get better, it's fine if you want to do less of the dot drawing. But it may help you keep everything straight as you go. Make sure that it's very clear what your answer is. I didn't draw lines through these first two, so it doesn't look like those are my answers. If you had drawn lines, then you would need to like circle this and say this is my answer or something. It needs to be very clear what your answer is whenever it comes to test time when you got to graph those by hand. Okay. Any questions on example 1? All right. Let's do example 2. Okay, we're still dealing with the same parent function. We've got x squared as our parent function. And so we've only got one transformation here. And let's see. Is it Aubrey or Audrey? Audrey. Okay, Audrey. What is our transformation that happens here? What? Vertical. Good. Vertical expansion by a factor of 3 in this case. Now, I don't really need to do this, but I'm still going to make my table for a very specific reason here. So if I make that table for x squared, it's like if I do -3, -2, -1, 0, 1, 2, 3. -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Those are just those parent graph points that I have that I started with for the last problem because we're still dealing with a quadratic. Okay, the reason that I still wrote that table, even though we should be getting that in our head and not having to write it every time, is because for expansions and compressions, I find it really helpful. So, for, let's just write ourselves a little note here. For for vertical expansions or compressions multiply why did it not let me write the y coordinate by the factor. Okay, so if you have a vertical expansion or compression, we're taking that y-axis and we're stretching it. In this case, it's expansion, so we're stretching it taller. And so when you stretch something taller, it's going to change the y-coordinates, but it's not going to mess with the x-coordinates because that would make it wider or skinnier. So if we just take all of these y-coordinates and we multiply them by our factor, which is 3 here. So 9 times 3 would be 27. 4 times 3 would be 12. 1 times 3 would be 3. 0 times 3 would still be 0. 1 times 3 would be 3. 4 times 3 would be 12. And 9 times 3 would be 27. Okay? So now these are our new coordinates that have been vertically expanded. So some of these obviously don't fit on the graph anymore. Negative 327 is way too big. Negative 212 goes off of the graph, but it's not way too far off of the graph, so I'm just going to put it a couple spaces above here. Then I've got negative 1, 3. 0, 0 stays where it was at. 1, 3 is here, and then 2, positive 12 is here. So I can draw the line through the graph. That is my answer, and when I draw that in, you'll see that graph looks a lot taller and skinnier than it did before. Every point where this is 1, 1, it's now 3 times taller than it was. So it did have a height of 1, now it has a height of 3. This one did have a height of 4, now it has a height of 12. So it stretches everything upwards. I think expansions and compressions are really hard to do just by looking at it, like we do the reflections and the shifting up, down, left, or right. So that's why I usually just write the table out for those. But if you can do it in your head, please go ahead. If you can do it in your head and get it correct, get it correct. My Math 1 class is full of kids who always want to just do everything in their head. And then they get the answers wrong every time. I tell them they can only do it in their head if they're getting it right. Okay, questions on example 2? Alright. Okay, example 3. Alright, here we're dealing with a square root function as our parent. Our parent is y equals the square root of x. So, Raphael, tell me one thing that happens to this graph. Good. Reflected. Over the x-axis. Let's see. Jennifer, what's something else that happens to this graph? Up 3. Very good. And see, here's another one of those 3's that's at the front, but it's separated by that minus. So it's a positive 3, so it's up 3. And then, let's see. Sydney Claire, what does that 2 do to the graph? Horizontal. compression by 1/2. Very good. Okay, so that takes care of all of our transformations. Here, you must do reflections and compressions or expansions before you move this up to 3. So we're going to do that first. I like to just go ahead and get the expansions or compressions out of the way because I think they're the most difficult. So first of all, though, we need to think about the parent graph because we haven't done the square root of x yet. Okay, so let's make ourselves a table. Since we got to do a compression, we're going to kind of need it anyway. Now, with the other problem, I started with -3. I could have started with -4 or 5 or 6, but those numbers, when you square them, are much too large to fit on the graph. If I try -3 here, what is the square root of -3? I can't take the square root of -3, right, because it's a negative number. We can't take the square root of negative numbers. We get i's whenever we do it. It'd be 3i. You can't graph I. So any negative numbers are not going to work here. So we're not going to use any negative numbers. We're going to start at 0. What is the square root of 0? 0. What's the square root of 1? 1. All right, now, here's our problem. The next number would be 2. What's the square root of 2? Without a calculator, which you're not going to have, you can't do anything with that, right? So let's skip 2. 3. Square root of 3? Can't do it either. What about square root of 4? That's 2. So 4, 2. All right. And then what's the next number that we can take the square root of? 9. So the square root of 9 is 3. You'll notice that these numbers are kind of switched from the quadratic. That's because quadratics, squaring something and taking a square root, are inverses of each other. So here I'm starting off with 0, 0, 1, 1, 4, 2, and 3, 9. It kind of looks like a quadratic turned on its side, except for it's only got half of it because we can't have those negative values. Now, for the last problem, we did a vertical expansion by a factor of 3, and we multiplied all the y's by 3. Any guesses of what we'll do whenever we have a horizontal compression? We're going to multiply the x's by our factor, okay? So let's write ourselves a note down for that. For horizontal compressions or expansions, multiply the x by the factor. Okay, so for this, instead of multiplying the y like we did on the last problem, we're going to multiply all these x's by 1/2. So 0 times 1/2 is still 0. 1 times 1/2 is 1/2. 4 times 1/2 is 2. And 9 times 1/2 is 9/2, or what is that as a decimal? 4.5. Okay. So if we graph these points, 0, 0 stays right where it's at, but 1/2, 1 would be about right here. Estimate a little bit. Notice how it's squishing in closer to that y-axis. Then 4, 2, it's going to become 2, 2. So this point right here squishes in. And then 9, 3, it becomes 4.5, 3. So you can see how it squishes in there. Okay, so that takes care of our horizontal compression. Still not done though, because we've got other things to do on this. Okay, questions so far? All right, I think that's the hardest thing to do. After this, I think it's a little bit easier. You're going to next reflect. You got to do that before before you move this up or down. So you're going to reflect these points over the x-axis. Flip everything upside down. And now all of those red points that I have there, they need to move up 3. So, purple here. 1, 2, 3. And then we'll draw in the rest of the graph. Make sure on the square root, don't go past this point right here, because that's that stopping point. Like if you think of the original, we didn't go below 0, so don't go past this point whenever you're drawing it in. So that purple line there is my answer. Questions? Okay. All right. Oh, gracious. This one looks terrible. If we look at everything here, we've got the 1/3, 3, the 12, the 7. Oh, man, this one looks really bad. What is the parent graph for this one? This is y equals x, which is a linear function, right? So, whenever your parent's function is y equals x, a linear. Okay? When your parent function is y equals x, when it's linear, don't use transformations, okay? Because we know a better way. In Math 1, how did you graph lines? Over and up, and the formula we used was y equals mx plus b, right? Use y equals mx plus b, okay? Every year, I always find it really interesting. I haven't had you guys long enough to have any clue how it's going to end up. But pre-cal is usually I have 2 semesters of it, so it's sort of split half and half. And I'm always interested to see whether first semester or second semester is going to be smarter, because usually one of them is smarter. Now, if you guys are smarter than first semester, then you're a really smart class, because they were a really good class, had higher test scores than I've had in a long time. So they've set the bar high for you. They were also the first class ever to all get the linear question right on the quiz. So whenever you have a linear question, you really just need to do y equals mx plus b. And we're going to do it here in a second, and it's really easy. However, when you see it and you're in graphing functions and transforming mode, sometimes you don't really realize what's happening here, and you try to do it the other way, where you've got a vertical expansion by a factor of 1/3 and a horizontal compression by a factor of 1/3, and then I think this actually moves to the right 4 instead of 12, which you don't even know about because I didn't teach you that, and then up 7, and then that would be terrible to try to do, right? So these you want to just graph with y equals mx plus b. So I have offered to all of my classes, as long as I've been given this type of quiz, I have offered to my classes that if every single person in this class gets the linear question right on the quiz tomorrow, then I will give everybody in the whole class 10 extra points. So you'll get 10 points. I mean, you'll get the points for getting the question right, of course, but you'll also get an extra 10 points. So that means you could make 110 on the test, on the quiz. So last year's class was the only class I've ever had actually do it. Every other year, and I've been doing this for a while, offering the same thing for several years, probably 5 or 6 years. They were the first class to ever actually all get it right. Okay, so it's really, I'm going to show you how to do it here in a second. It's really not that difficult. but you've got to remember that this is what you've got to do. And that's what gets everybody. Everybody always tries to, I see dots all over. When I used to, I've only given this online the last 2 years. I used to see, like whenever I gave it on paper, I'd see like dots all over the paper where everybody's trying to transform it. It's really going to be a mess if you try. So if we're just doing y equals mx plus b, we just need to get this in y equals mx plus b form. So we would just distribute that 1/3, and usually, especially since this is calculator inactive, I'm pretty kind to you. I'm going to at least make sure this number right here is a whole number. So 1/3 times 3 is just 1, so we get 1x, which is just x. And then 1/3 times 12, a third of 12 would be 4. So we get x minus 4, and then we got that plus 7 over there on the end. And then that's y equals x plus 3, whenever I combine that negative 4 and the positive 7. So now, there's not a 1 here, but I could write it there if I wanted. I have a y-intercept at 3. That number right there is my y-intercept. I have a slope of 1, and that's not a fraction right now, but I could make it a fraction by putting it over 1. So I'll go up 1, over 1, up 1, over 1. Like this. I could also go in the other direction. And I'm just going to draw in that line right there. Okay, so questions on that? Back to math 1, just y equals mx plus b, but you got to remember that that's what you've got to do. Okay, and there is one, of course, on the quiz tomorrow where this is what you got to do. All right, let's go on to example 5. For example 5, we've got, here we've got absolute value of x is our parent function. Andrew, tell me one thing that happens to this graph here. Okay, very good. Up 5. That 5 right there is positive, even though it's out front. It's not multiplied, so that's our up 5. Patrick, something else. Okay, good. Left 2. Let's see. Brittany, what else happens to this one? Yes. Yes, reflected. Over the x-axis. And let's see. Jackson, what about that 3? What's that 3 going to do? Vertical expansion by 3. Okay, so absolute value is pretty simple to graph the parent graph. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. 3, 3, 4, 4, 5, 5, and so on. If I take the absolute value of negative 1, I get positive 1. Absolute value of negative 2 is positive 2. Negative 3, positive 3. And we just get that V shape that has a slope of 1 in the first quadrant and a slope of negative 1 in the second quadrant. So that's the parent graph that we're dealing with. I could reflect it if I wanted. I like to just go ahead and get those expansions and compressions over with first. So I think I'll do this. I'm going to make myself a table, but only for the right-hand side, mostly because I just know I can just flip it over, right? So 0, 1, 2, 3. I'm not going to go out too far because it might run off of the graph, and I can just keep the pattern going here. So I got 0, 0, 1, 1, 2, 2, 3, 3. That's what we're looking at right now. Okay. So Sydney, what do we do when we have a vertical expansion? What do we do with those numbers? Okay, we multiply by the y. So that 3 right there, we're going to multiply by the y. So this stays 0. We'll have 3, 6, 9. Good thing I stopped at 3 because the next one would have gone off the graph anyway. So instead of 0, 0, well actually 0, 0 stays where it's at. Instead of 1, 1, we'll have 1, 3. We'll have 2, 6, and we'll have 3, 9. And then I didn't do both sides of this graph because I can just reflect those over the y-axis, x-axis, y-axis, and get the other side because of the symmetry of this graph. Okay. Now, Chase, if I just look at the right-hand side of the graph here, what's the slope of that line that we have there? Flip it. It's right. Y's go on top. So 3 over 1. Right? I've got a slope of 3 over 1. So rise over run 3 over 1. On the left-hand side, it's negative 3 over 1. So notice that whatever number, my factor right here, it just ends up being the slope of the line on that side. Now, this is only for absolute value. Don't do that for quadratics or cubics or other things. You're going to need to use the table for that. But for absolute value, it just ends up having that same slope. So if you want to use that instead of doing the table, you could do that. Okay. So that takes care of our expansion. Now we need to reflect it over the x-axis. So I'm just going to take all those green points and flip them upside down. And now, once we do that, all of our new red points, they need to go up 5 and left 2. So we'll take all these points, we got to go up 5, left 2. So 1, 2. And then we can draw in our graph there. Questions? Okay. Let's look at 6. Alright, 6 is weird. These are these weird ones that we looked at the other day. So, what's the parent graph? It is y equals x squared. How many of you were thinking absolute value of x? Many of you, maybe some of you that won't admit it, but I know some of you were. So y equals that. Our parent graph here is y equals x squared. Okay. The absolute value bars here are a transformation, not the parent graph. Now, if we go back to the one we just did, notice inside of those absolute value bars, all I had was a plus 2, an x plus 2. I didn't have anything strange like a square or a square root or a cube or any of those, or like a fraction or anything like that. Just x plus 2. Okay, so that just moves it to the right 2. So the parent graph was an absolute value here. If you have anything strange on the inside of the graph, besides just an x or a plus 7 or like maybe a 3x or something like that, then the absolute value bars are not your parent function. Okay, so what we have to do for this is we have to completely ignore the absolute value bars at first. Okay? We have to pretend like they're not there at all. So if they're not there at all, then the 7, does it move it up, down, left, or right? Okay, I'm hearing right. I'm hearing down, and I'm hearing right. Okay, those would be the two logical answers to have. Let's take a vote on it. How many of you think that the -7 moves the graph down? Raise your hands high if that's what you think. Okay. All right, how many of you think it's right? Okay. All right. Down is correct. Okay. The reason being is because absolute value bars are not your parentheses here. They're a transformation. So your parentheses are right here. Okay. So you don't have parentheses, but they would be right there. So this is the quadratic. It has been moved down 7. Okay. So we would take a quadratic. It looks like this. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And then it's symmetric, so we could just put the other side over here. All right, so we would take that quadratic and we would move it down 7. 1, 2, 3, 4, 5, 6, 7. Now, I usually do not draw in the line for these until I'm at the very end and I've got my answer, except for on these problems and also on the rationals. I also draw lines sometimes for those. So I'm going to go ahead and draw in the line even though I'm not done right now. Okay, this is not my answer, but I'm going to draw the line for an important reason here. All right, so whenever we take the absolute value of this function, what it's going to do is it's going to take anything below the x-axis and flip it upside down over the x-axis. But anything that's above the x-axis stays where it was already at. So that means I'm going to use red for my final answer. And since I've drawn a line, I'm going to put final answer over here. Here's my line in red. So that means this part of the graph and this part of the graph, they just stay right where they were at already. But all of this green stuff that's below here, it's got to be reflected over the x-axis. So this point right here will be here, this point. I'm going to erase those original blue dots just because they're, so we can see a little better. So what I did is I took all these green dots that fell below the x-axis and I flipped them upside down. And then my red line is my answer, so now I'm going to trace through those dots. Make sure you go all the way to the x-axis. And we're going to trace it and we get this weird sort of W looking graph. This could happen with any type of equation. We're mostly going to just look at quadratics. We won't get too complicated with these types, so you'll probably see one. Typically, I've moved the quadratic down first. It could go down and to the left or down and to the right. I don't move it up usually because if it moves up, then it is all above the x-axis and doesn't look any different. So but you'll see those weird W looking shapes for those. Okay, questions? Yes. Very good question. In this case, since those absolute value bars are on the outside of everything, like if you're thinking of order of operations, you do whatever's on the inside first, and then at the very last you would make it positive because of those absolute value bars. So this would be the one case where you don't do the reflection first. If it is just a straightforward reflection over the X or Y axis, you do that before you shift anything up or down. But for the absolute value bars where you're only reflecting that negative part, you're going to do that last. Okay. Okay, any other questions? All right, so we got a couple more here. Okay, so for this one, I'm gonna go through these last couple kind of quickly, so you guys can have a little bit of time to work on your assignment. So for this one, our parent is a quadratic again. And this minus 3 is going to move the graph down 3. And the 1/2 is on the inside, so it is a horizontal. Expansion. And it's going to be by a factor of 2, because if we do 1 over 1/2, dividing fractions is easy as pie. Flip the second and multiply. 1 times 2 over 1 is 2. So we're starting from that same quadratic that we've done several times now. I tell you what, hold on, let's change something here. Make that a cubic, because we need to do a cubic, because there's some on your homework, and I should have put one on here. Let's make that, mark out your little square and make that a cube. Doesn't change anything about our expansions, compressions, that stuff is all still true. We have not done a cubic yet. Let's do a cubic x, y. I'm going to start at -2 here because 3 cubed is too big to fit on the graph. What is -2 cubed? Is it 8? It is -8 because that's -2 times -2 times -2. And so -2 times -2 is +4 times -2. So we would get -8. So whenever you cube something, it is going to keep the sign. Whereas with a square, sign goes away. So we'll have -8. And then -1 squared, cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is +8. All right. So that parent function we're looking at looks like this. Right here. And we always want to do our expansions or compressions first. So if we have a horizontal expansion by a factor of 2, horizontal tells me I'm going to multiply the x. Okay, so I'm going to multiply the x by 2. So this will be -4, -2. This will still be 0. I'll have 2. I'll have 4. And so I've got -4, -8, -2, -1, 0, 0 stays where it was at. 2, 1, and 4, 8. all of these points need to go down 3. So I take all these points down 3. Go off the graph a little bit. And then my final answer looks like this. Questions on that one? Alright, one more, last one. Rationals are my least favorite to graph, I must admit. I do not like graphing them because they are my least favorite to graph, and I think that they're a little complicated to look at. I'm pretty much only going to give you vertical and horizontal shifts on these. I will not make you do expansions or compressions for the rationals if you're graphing them really by hand or not. I might give you some where I ask you about them and you have to tell me in word form that there was expansion or compression. But as far as looking at the graph, they are kind of complicated, so I'm probably not going to ask you about that. So the parent function for a rational is f of x equals 1 over x. So if we make ourselves a chart for that, here's your problem. Like, if you plug in 0, what's 1 over 0? That's undefined, right? So we can't really plug in 0. I could plug in, I'm going to leave myself some space here. I could plug in 1. 1 over 1 is 1. There we go. Got a good point there. Now if I plug in 2, I get 1/2, which is right here. And then 3 would be 1/3, which would be right here maybe. And 4 is 1/4. Now, you can't really graph all of those points very well on these graphs. 5 would be 1/5, 6 would be 1/6, 10 would be 1/10, 100 would be 1/100th. So what, as we continue on, that number gets smaller and smaller and smaller and smaller. What number does it get close to? It gets close to 0, right? Is it ever going to become negative? It will not. It's not on this side of the graph here. So what happens is the line of the graph goes out like this, and we have what we call a horizontal asymptote. Have you guys heard that word before? Horizontal asymptote. A few of you maybe. So it gets closer and closer and closer to that line. And so the same thing happens right here vertically as well, but we have a vertical asymptote. Because if I plugged in, for example, if I plugged in 1/2, then that would be 1 over 1/2, which dividing fractions is easy as pie. We flip the second and multiply, so 1 times 2 over 1, we have 2. And if I had 1/3, I'd get 3. If I had 1/4, I'd get 4. So in this direction, we're going to get closer and closer and closer to the point as well. And then for the negatives, I'm not going to do the chart, but for the negatives, you would have the same thing happen, but in this third quadrant. And so it would look like this. Now this is just the parent graph. This is not the answer. This is the parent graph. Now, for most of the other problems, I would like you to have at least 5 points for your absolute values, for your cubics, for your quadratics, all of those. I'd like for you to have at least 5 clear points that I could see if it's one where you're graphing by hand. On these, the only 2 points that I require you to have are these two right here. But you do need to have the vertical and horizontal asymptotes correct. I, a lot of times, like to actually draw them in. So if we draw them in here, have a dotted line, let's make that blue. So it's not actually part of the graph, but I know right there is my vertical asymptote and right here is my horizontal asymptote. I like to sort of draw them in so that I don't cross that line. You don't have to draw them in, but you better not cross that line. Okay? So for this problem, I just need to go up 4 and to the right 3. So if I move this graph up 4, it's going to move that horizontal asymptote up 4. And it's going to move that, not that. It's going to move that vertical asymptote, not that either. There we go. It's going to move that vertical asymptote to the right 3. So I usually just move my asymptotes, which I've messed up here because I moved the graph. I move those first, and then I'm just going to graph that point in this, what would be the new first quadrant, and then this point here. There's a chance on those I might would give you a reflection over the x-axis. If you had that, then it would just be, instead of being like in the first and third quadrant, you'd be in the second